Michael.
Yeah, hello. If you are scared by the numbers that you have heard from my previous speaker, from Alan from DVS, about 1.5 gigabyte per frame in 15 frames per second, you can relax. We can also go slower and with lower resolution, making that data flow much easier. So my presentation contains two slides at the beginning talking about the technology that we use. So I keep this brief. I don't want to pour too much technology onto you right now. The second part, which is larger, contains a few examples of films that I have had in the last year or so, which shows problematic archive films. So this will be the major part of the presentation. Starting with the first part, I want to give you an overview of the technology that we use. I have heard the word Scanity a few times already, so I can guess that some of you know the Scanity very well, and some at least have a glimpse of what it do. So the technology that we use is in many cases very unique. For example, the TDI sensor that we use, that is a new technology that allows us to scan very fast with still very low light levels. And this is a TDI sensor that uses 96 lines instead of one line, and all the lines are accumulated, making a very strong and virtually 96 times stronger signal. And therefore we can use just a few LEDs to illuminate the film, although we scan very fast. So instead of having a xenon bulb with a 750 watt light, we use simply a few LEDs on this little lamp or board that you see here. Scanning fast with LEDs is also not known so far with regard to technology. Another part is a new design of a gate, and we're using a roller gate. That means the film is not slipping on skid plates or any stationary mechanical part where you can cause abrasion and can produce dust. So this gate contains two rollers, and the edges on the film are running on the rollers through the gate and never touching any stationary part. So whenever the film is touching the machine, it is just rollers. Also very unique. And another important thing is the optical detection of the perforation holes. So instead of forcing pins into the perforation holes of the film and pushing the film or the frame into the right position to be steady, we just scan the perforation holes and use this information in order to shift the image, the digital image, in a frame store rather than physically the film frame, which allows us to scan fast, which is more smooth to the film and more safe to the film. And for doing that, and doing that all in real time or while we scan, we also have a very high sophisticated, dedicated processor with 7 FPGAs on it, who is doing all the processing that is necessary in the machine. These features allow us to have very nice features which others don't have. For example, speed 15 frames per second in 4K or 25 frames per second in 2K is by far the fastest scanner that is available. Pin-registered steadiness optically, I mentioned that already. A gentle and safe film handling is very important, especially for fragile and brittle films from the archive. The versatility of applications ranging from DI, from daily scan, to digital digitization of archive stuff is very large. The range of formats, the range of film formats, data formats, is very large. So this machine is very versatile. Of course, and this is a thing that you have to have, otherwise you are not in business, is the high image quality. We have a high dynamic range. we have high resolution beyond 4K, and we have a color reproduction which is really dedicated to individual films individually and can be adjusted on RGB level based, and this allows us to have the high quality. So, and this technology and these features also makes us proud to have sold this machine more than 20 times in the last almost 2 years. So everybody has such a slide. I have seen that, and you see a few names repeating all the time. So far to the technology and to the features of the machine. Now I'm coming to the next part of the presentation, which gives you a few examples of films that came across either during exhibitions or when customer visits our facility with these films. And these films, or these archive films, can show a lot of different problems. And you may know them very well, and we have learned those in the meantime and have solutions for all these kinds of problems. Shrinkage, warping, bad splices, damages, notched or broken films, vinegar syndrome, faded colors, dirt and scratch, film grain, sensitive base, nitrate film material, sound on the film, and overscanning in terms of the frame bar is moving in and out. So we have to have solutions for all this kind of problems, and we have. And a few things I would like to mention here. So due to the fact that we have a very tight control on the film when it's running through on the film deck, we can measure the shrinkage permanently and give you an indication on the shrinkage of the film. So this is just more or less an information, but it's important to know that the shrinkage of the film in longitudinal direction can be as almost unlimited. So, but the vertical shrinkage of the film has the maximum of 4.0%. So then the film will fall off the rolls in the roller gate. But usually 2% is a very high shrinkage already, and the worst film I have come across was 2.5. So you are very safe with 4.0 shrinkage for a film width. But in longitudinal direction, we virtually have no limits. So it can be shrunken as hell due to the optical perforation detection. So I don't need to go this. I went through this verbally. Another thing is warping and buckling films. I have a few photos of how film can look like, and we can still produce very nice and sharp images on this machine. This is a sample of a 35mm film from a Brazilian archive that we scanned. So, due to the fact that the film runs on this roller, when you bend the film over the roller, all the warping and wobbling and bending is taken out by the curvature of the film, and the tension of the film in the roller that flattens out that image in an optical area. And due to the fact that we have a line sensor, we only have to have it flat for a line rather than the whole frame. And this is very well supported by the roller gates. Another important thing is that the optics that we use is built so to have the maximum of the focus depth. So it has a small aperture, which usually consumes a lot of light. But due to the fact that we have such a high sensitive sensor, we can afford to have an optics with a small aperture, resulting in a large focus depth. Also important to have a very good sharpness, left, center, right, and of course top and bottom as well, because this is a line scanner. The design of the roller gate is also very tolerant to all kinds of damages on the film. and including bad splices. Even this film, this is again the Brazilian film, we have not noticed that this splice was torn apart, but we let it run through the scanner, and it did not stop the scanning process. It did not went out of scanning. It did not tear the splice any further. It still remained like that was after scanning the images. So even this very drastic examples shows you how smooth and how tolerant the scanner is with regard to damages on the film. That also means if you do a restoration, if you want to restore a film, the work that you need to do prior to scanning the film, is much less than you used to do in the past. This, for example, was a test film that was torn, and when we scanned it, this image came off the scanner. Yeah. So of course you see the tear, but it does not stop the transfer. It does not break the film any further. So you may ask what happens if some perforations are missing and the perf camera does not see perforations. How does this machine continue scanning? There's a lot of redundancy in the machine, such as electronic flywheels, that synthetically generate the pulses that are usually coming from the camera in case the camera does not see the perforation hole. So that works very smoothly, even if the perfs are missing for several frames.